Hello, hello, Sasikant.
Yes.
Okay, so am I audible? Is my screen
Yeah.
visible? Okay, fine. Okay, so there are no others. Let's wait for 5 minutes, then we'll start.
Okay. I have a simple query for calculus. Can you? Hello.
Yes.
Can I ask a question from calculus? It's a simple question of limit.
Okay. Yes. What's the question?
I'm touching on text.
Okay. So for a function, only things matter are domain and range. Okay. So codomain can be anything. It will be just larger than the range. It will be either range or something bigger than the range. It can be anything. So when we define a function, okay, let's see this screen here. Okay, so when we say that, what do we do for defining a function? We say that f is a function from some set A to some set B. Okay, so whatever set we prescribe here, that is called codomain. It can be anything. And whatever set we prescribe here on the left hand side, that we call domain. So A is our domain, and B we call a codomain. Okay, but range of a function is something that is related to f. Okay, so what is range? So that's denoted by r of f. So range is all those points.
What are mapped from A, right?
Okay, so map is from A to B, and range of a function, all the values of function where x belongs to A. Okay, for all the domain values, you take anything from the domain x and take what are possible images it can have inside B. So this range of function is always a subset of B. Okay, so you can what you can do, you can always write the same function as from A to this range of function f. Instead of B, you can you can make your codomain smaller. Okay, so now in this case your codomain and range are both same.
Okay.
Okay, and the same function f. Okay, let's say if B is contained in something, some set C, and B is like C is strictly bigger than B. Now again you can write the same function from A to C also, right?
Okay.
Even though we are increasing, we are making larger this codomain, but still the range will be same, because the range is the set of all those values which function can take. These are set of all images of the function,
Okay.
right? So they will not change because A is fixed.
Okay.
Because A is fixed, that's why range will not change.
Okay.
So whatever we write on this right hand side, that is called basically codomain.
Okay.
Okay, let me see if there are other people. Otherwise, we will just start. Okay, there are no one. Okay, then. So should I start this tutorial?
Yes, you can.
Okay. Okay. So welcome everyone. So this is the live session for fifth week, and we will discussing the problems related to the whatever material that has been covered in the fifth week. Okay, so most of the problems for this particular week is related to about the improper integrals, so convergence and divergence of improper integrals. And at the end, there are one lecture video related to beta and gamma functions also. So we'll see one or two problems for related to beta and gamma function, but mostly we will be discussing about convergence and divergence of improper integral. Okay, so what are improper integrals? So okay, so whenever so before defining improper integral, first let's see what are proper integrals. Okay, so integral is said to be proper whenever the this area is defined. So area, because we know that the integral gives the area of the function, okay, between below the graph of the function. So whenever this area is defined, we say that the function is proper. So defined in the sense that, okay, let me not call define. So this is the definition of proper integral. Okay, so whenever function is bounded, so this function is bounded, and this range of the integral, this upper limit and lower limit a to b. So we are integrating the function from a to b. So when a and b, these are finite values. Okay, so a and b, let's say they are real numbers, and both a and b lies in this range minus infinity to plus infinity. Okay, so that is called a proper integral. But what happens when one of the condition is not true? Okay, so if either function is not bounded, a function becomes unbounded, or one of the values, this upper or lower limit, becomes infinity. In that case, that kind of integral, we say that it's an improper integral. Okay, so and based on this boundedness of either function or this range, we define them in two categories, mostly first and second. So if the function is bounded, but either a or b is infinity or plus minus infinity, then we say that this is an improper integral of first kind. Okay, note that for this one of these values, a or b, this must be infinity or minus infinity, and the function should be bounded for an improper integral to be first kind. Okay, but if function is unbounded, but these values are finite, a and b, these are not infinity, so a and b, these are finite values, but function become unbounded at one or more of these points. Okay, so function is bounded in the interior of the range, but it may be unbounded at the end points, either upper limit or lower limit. Then we say that it's a second kind of integral, improper integral. Otherwise we say that the third kind of integral, or mixed kind of improper integral. Okay, so let's see one example. Okay, so this is the one of the problem, and you have to find which kind of integral it is, and if it is converges or diverges. Okay, so convergence means this integral have some finite value, fixed value, even though the range is infinite, but the value of the integral is finite. Okay, but if value of the integral is infinite, then we'll say that it diverges. So which kind of integral is this? Can you tell me? Okay, so notice that this b,
It
why?
goes to infinity.
Okay, so range is the upper limit is infinity, but function may be bounded, right? Okay, so one more thing, we take this function to be bounded in the interior, so we will not go to infinity. We take this function to be bounded in interval a comma t. Okay, where t is less than infinity. So we say that function is bounded in this interval a comma t for every t.
I didn't watch the lecture.
For all t less than infinity.
I didn't watch
Okay,
the
so
lecture.
in that sense,
So
this
not
okay, okay, okay. So in that sense, function is actually bounded. Okay, if you because the function is defined from 0 to infinity, so if so it will be, so I'm actually not drawing the graph of the function. I'm just saying that from 0 to some t, if you fix some value of t, then up to that point function is bounded. It is not going to infinity. It is something. Okay, it is not going to infinity. Yeah, at the end it will go to infinity when t approaches to infinity, but otherwise not. because this x, you know that it will go to infinity. So actually, it's a improper integral of first kind. So the answer is correct. Now you have to find if the integral converges or diverges. So convergence means the integral should have some finite value. Now how to find that finite value? So how do we evaluate the improper integrals of first kind? So this is one of these are some way you can evaluate these integrals. So if let's say this upper limit is infinity, so what do you do? Replace this infinity by some finite fixed number, let's say r. First compute that integral and then take limits r tend to infinity. Okay. So for this particular integral, what we will do? Okay, so we have to find what is the value, or if integral converge, this integral converges or diverges of this function e to the power minus x square dx. Okay, let's so by definition, this is same as limit r going to infinity and 0 to r. Okay, now we have made it to a proper integral. You can see that now it has become proper integral because the function is bounded in the interval 0 to r and both endpoints are finite. Okay, so now and after finding this value, we will take limit r goes to infinity. Okay, so what you can do, you can change this variable x square. Okay, when you change this variable, what will come? You can put x square equal to t, then you will have 2x dx is dt, right? So you can replace dx by x times dx by dt. So this you have x times dx. Okay, so this is half of e to the power minus t dt. Okay, so when x becomes 0, t will become 0. When x become r, t will become r square. Okay, so now what is the value of this integral? It is limit r going to infinity. So you can integrate e to the power minus t, right? It's half of minus of e to the power minus t from 0 to r square. These are limits, upper and lower limit. Okay, equal to limit r going to infinity half of. Okay, what will come after you put r square and 0, upper limit and lower limit? These are not upper limit or the endpoints, upper endpoint and lower endpoint. These are okay. So when you put 0, you will get 1. So this is 1 minus e to the power minus r square. Okay. So what is the answer? It's half, right? Because e to the power minus r square goes to 0 as r goes to infinity. So when you take the limit r tends to infinity, this e to the power minus r square, it goes to 0. Therefore, the value of the integral is half, and hence the integral converges. Okay, so I can write here I converges. So this value half. Okay, so the what are correct answers? A and C are correct. Okay, so okay, now see, this is second problem. Now what kind of integral it is? First, you have to identify what kind of integral it is. If it is either first integral of first kind or second kind. Okay, which kind of integral it is?
It should be first kind, sir.
Okay, so remember in the integral of a first kind, you must have one of the endpoints infinity. At least one of these endpoint must be infinity or minus infinity because these are both finite. It cannot be a first kind of integral.
Okay.
But let's see if it is a second kind of integral. So when a integral, we say that it's a second kind when the function becomes unbounded at certain points of this range, right?
Yes.
Okay, so what is tan of twice of pi by 4? Okay, we were calculating this value of the function. This is our function at endpoint. So what is tan of 2 times pi by 4? It's tan of pi by 2. What is tan of pi by 2? It's not defined, right?
Yes.
It's infinity. So basically the function has become unbounded. That's why it's an improper integral of second kind. Okay, now we have to find if the integral converges or not. So basically, if the function, this integral has a finite value or not. Okay. So let's see how do we evaluate the improper integrals of second kind. Okay. So what we will do, because there is a problem at some point, right? So both of these points there is a problem. Okay. So if you evaluate at another point, 2i's of minus of pi by 4, the lower end point, then what you will get again minus infinity, right? It's tan of minus pi by 2.
Yes.
Okay. So because there is a problem at both the end, so this is kind of graph which tan x has. So here these are asymptotes where the function becomes infinity. This is pi by 2 point and this is, let's say, minus pi by 2 point. Okay. So because there is a problem at this end point, but what we do, we take some value which is smaller than pi by 2. Now there is no problem, right? Because the function is defined, this area can be find out, and we take some value bigger than minus pi by 2, something bigger than pi by 2. Now there is no problem because the function is again defined and this area can be calculated. So that is our idea to evaluate the integrals of second kind. Okay. So if there is a problem at b, let's say the function becoming infinity at x going to b. So what we will do, we will take something smaller than b. Something smaller than b means we will subtract something from b. So this is b minus epsilon, and then we will take limit epsilon goes to 0. Similarly, if there is a problem at lower end point, like the function becoming unbounded at x goes to a, so what we will do, we take something bigger than a. Something bigger than a means this a plus epsilon. We have added something, okay, small quantity, and then we are taking the limit epsilon tends to 0. What will happen if the function is becoming unbounded at both the point, let's say at a and b, because that is our case. Okay, so again the same thing. Now there are two parameters, epsilon 1 and epsilon 2. We're taking something less than b and something bigger than a, and after calculating the integral we will put this limit that epsilon and epsilon 2 both goes to 0. Okay, so this we will do for this question. We have to find this I equal to minus pi by 4 to pi by 4 tan of 2x. Okay, now this integral can be written as minus pi by 2 to pi by 2 twice of tan x dx. Okay, why? Because we can always put 2x equal to t, and then dx will become dt. Twice of dx is dt. Okay, so it is 1/2. Okay, just replace dx by dt by 2. Okay, and then endpoints will become minus pi by 2 to pi by 2. Okay, now to evaluate this kind of integral, what we will do, take something bigger than, let's say, epsilon 1, something smaller than pi by 2, let's say epsilon 2, and then we will take this limit, here half is there, epsilon 1 and epsilon 2 both goes to 0 of tan t dt. Okay, so what is the integral of t? First let's find what is the integral. Do you know what is the integral? Okay, so integral of tan function is minus of log of cos t. Okay, and then you will put this upper limit and lower limit. What is lower limit? Minus pi by 2 plus epsilon 1 and pi by 2 minus epsilon 2. Okay, and this is half, and then limit epsilon 1 and epsilon 2 going to 0. Okay, so when you put these lower points and end points, when you calculate this integral at these points, what we will get? So let limit epsilon 1 goes to 0 and epsilon 2 goes to 0, half of. Okay, so we will have log of cos minus pi by 2 plus epsilon 1 and minus log of cos of pi by 2 minus epsilon 2. Okay, this is the limit. Now we can use these well-known trigonometric identities. This will become log of sine epsilon 1 minus log of sine epsilon 2, right? Now notice that this limit is infinity. This limit does not exist, or we can say that this limit that does not exist. Why the limit does not exist? When you take epsilon goes to 0, the sign of epsilon 1 becomes 0, but log of 0 is not defined, so it will go to minus infinity. Okay, so the log function is not defined at 0, so it's unbounded. So the limit does not exist, and hence the integral diverges. It does not converge. So here we have one example where the integral does not converge. So we can say that I does not converge. Okay, so the B and D answer are correct. Okay, let's see the fourth problem. Again, what kind of integral it is?
The first kind.
Yes, so this is the first kind of integral. Again, let's see if the this integral converges or diverges. Okay, so we will use again the same comparison test. So this is that comparison test for improper integrals of first kind. Again, you choose some function and you take the limit x tends to infinity of this fx over gx, and if this turns out that limit turns out to be k, which is non-zero, then both of these integrals, the improper integral of fx and gx in this range, they will either converge or diverge. Okay, so their behavior is same. Okay, for this particular function, okay, so in this case, what is our fx? This is 1 over x square 1 plus e to the power minus x. Okay, so we will take gx as 1 over x square, and let's find what is this limit. Limit x tends to infinity fx over gx. Okay, so when you divide fx by gx, this x square will cancel and you will get that limit x goes to infinity of 1 over 1 plus e to the power minus x. Okay, so when you take x goes to infinity, this e to the power minus x, this function goes to 0, and therefore this limit is equal to 1. Okay, now you can say that by limit comparison test, the integral which was from 1 to infinity fx dx converges. As why this integral converges? Because the integral from 1 to infinity of 1 over x square dx, this converges. Okay, note that we have said that when this limit is become non-zero, then both of the integral have same nature. They will simultaneously converge or diverge. Now from these test integral, we know that 1 over x to the power p dx always converges whenever p is greater than 1. And in our case, this p was 2, right? Because this is the integral 1 over x square. And therefore, we get the convergence of this integral.
See then.
So are there any questions?
No, it's also I have a question of confusion because I'm not comfortable with calculations with e in calculus.
Oh, okay.
Can you explain me the uses of e and how we calculate e questions like? I mean, this is not related to exactly.
So it's just a function, like there are lots of functions, so it is another function. Okay, so this function is defined at e to the power x. So e is some number, right? So you have numbers, right? You find the power of 2, so you get 4. You have power of 5, you have something. 128, whatever. So these kind of functions you always have. You take a fixed number and you keep on taking its powers. So it is like that, but it is little bit different in the way that this number e is a irrational number.
So
Okay, so
here the, no, the number is constant and the power is the variable.
yeah, power is the variable, number is constant, and the variable is not taking only integral values, it can take any value. Okay, the function is defined, this function is from real number to real number. Okay,
Okay.
so it can take any real values, and okay, so again see that we have written that function is from R to R. Okay, but the range of function is actually the image of this whole interval is 0 infinity. This functional is not also 0, it's 0 to infinity. The function is never 0. So fx is never 0, it cannot take any value 0, because power of e is will be always positive, the powers are always positive, so it is never 0. And when you take f of 0, means you take e to the power 0, then you will get 1. Okay, so the behavior of this function is like this is kind of graph of this function. So here at 0, you will have 1. So this is the point, 0, comma 1. Okay. So when x goes to infinity, right? When you go this direction, in this direction, x going to infinity, the value will become larger and larger.
Yes, sir, due to exponential.
Okay. But if you go in the negative direction, it will come very close to this axis, x-axis. Okay. So let's write only. Okay, so they will become kind of parallel. So when you go to in this direction, x going to minus infinity, so the functional values become 0, because it is very close to the x-axis. So we will have these limiting situations, that limit x going to infinity, e to the power x is infinity, and limit x going to e to the power x minus infinity, it is 0.
Okay.
But if you take limit as x goes to 0, then it will be 1, simply because you can simply put e to the power 0 and you will get 1. Okay, therefore in the previous problem, when you were taking this limit, right, what we are doing, we are saying that this limit is 1. Why this limit is 1? Because take this limit x going to infinity, e to the power minus x. Okay, so what do you mean by e to the power minus x? It is same as 1 over e to the power x, right?
Yes.
Okay, now this limit will become 1 over limit x going to infinity, e to the power x.
Yes.
Okay, so now this is kind of 1 over infinity situation, so you will get 0, the limit is 0. Okay,
Yes.
so okay, let's start with the next problem. Okay, so there is a term that is called absolutely convergent. So when a integral is absolutely convergent, okay, let's write that definition. So we say that the integral, let's say a to b, a and b can be infinity or finite values. We say that the integral this fx dx converges absolutely if the integral a to p, you put a modulus sign, you take the non-negative values, and if this integral converges, if this particular integral converges. Okay, so when the modulus of the function, you take the modulus and then you take the integral, if that integral converges, then you say that the original integral converges absolutely. Okay, and now there is a result that says that absolute convergence implies the convergence. Okay, so if an improper integral converges absolutely, then it will also converge. Okay, so in this particular problem, we have to find out if the given integral converges absolutely or not. Okay, so the integral is 0 to 1 sine 1 by x divided by x to the power half dx. Okay, now we have to find if this integral converges absolutely or not. For that, what we will do, we'll find this another integral, let's call it j, from 0 to 1, the modulus sine of 1 by x divided by x to the power half dx. Okay, now let's see if this integral j converges or not. Why this integral? So note that this we will use this comparison test, because sine 1 by x divided by x to the power half, this modulus is always less than equal to 1 over x to the power half, right? Why? Because the modulus of sine function, the maximum value is 1. Okay,
Yes.
and note that this integral 0 to 1 over x to the power half dx, this converges. Okay, because this is our test integral. Okay, remember this test integral, this is the test integral. Okay, and this in our case the b is 1 and a is 0, so this is 1 over x to the power p, and this integral converges whenever p is less than 1, and in our case the p is half. Okay, the p value of p is half, so therefore this integral converges. Okay, now use comparison test, because this function, so this is our fx, okay, and this is our gx. Okay, now fx is less than equal to gx, and integral of gx converges, and because integral of gx converges, we have the integral of this modulus of function fx is also converges. Okay, that is from comparison theorem. So we can write, since this integral converges by our comparison test, this integral j, so whatever j is, so the integral j converges, and hence the integral I converges absolutely. Okay, now we know that absolute convergence imply convergence, and therefore we have that I also converge, right? Why? Because absolute convergence
It's good. Converge.
implies convergence.
Converge.
Okay, therefore the options A and C, they are correct. So the integral converges absolutely, and hence it is convergent. Okay, what about question C? Does this integral converge or diverge? Okay, so we'll again use comparison test, this limit comparison test, which I have already discussed. Okay, so in this case, what is fx? It's 1 over x square plus root x, right? Okay, so this can be written as 1 over x to the power half. You can take x to the power half common, right? And then 1 plus x to the power 3 by 2. Now take your gx as 1 over x to the power half. Now note that the limit x goes to 0 of fx over gx is equal to limit x goes to 0, 1 over 1 plus x to the power 3 by 2, and this limit is 1, right? And hence now use this comparison test. The comparison test says that whenever you have this inequality and the limit of fx over gx is non-zero, this k is non-zero, both of the integral behave same. Their convergence and divergence are same. Okay, and hence by limit comparison test. Zero to 3 fx dx and 0 to 3 1 over x per half dx have same behavior. Okay, but we know that this test integral 1 over x per half from 0 to 3, this converges, right? Why this converges? Because as we have seen before, this is our test integral and the value of p is half, and in that case the integral converges.
Yes, sir.
Okay, and because they have same behavior, hence the integral from 0 to 3 fx dx converges. Okay, so we are just saying that this integral will have some finite value. So what we mean by convergence, the convergence mean that this integral 0 to 3 fx dx will have some value, some fixed value, let's say c, and that we don't know. That can be find out. If you want to know, you can work hard, you can find out. But we wanted to know if that value exists or not. Okay, so we know that this is true, so the integral is convergent, so statement is true. Okay, okay, let's go to the beta and gamma function. So beta and gamma function, they are kind of improper integral. Okay, so this beta is an improper integral of second kind, and this gamma is an improper integral of first kind. Okay, actually you will see that this gamma integral, this is a mixed kind of integral. Okay, so this is a mixed kind, third kind. And this one has first kind. No, not first, second kind. Why this integral? This is improper integral of third kind, because one of the value is infinity. Therefore, this is first kind. It says that it is first kind. And note that this function x to the power n minus 1, this will become unbounded. No, okay. So this is not, this is an improper integral of first kind, not third kind. Okay, first kind. Okay, because we have assumed that n is positive. Okay, if this n was negative, then there is a problem. Okay, so note that n is actually this is actually third kind. Okay, I was correct. Why this is third kind? If you put n equal to half, okay, so if you put n equal to half, then you can see that this is the integral is x to the power half minus half, right? At this place you will have x to the power half minus 1, half minus 1, so this will become x to the power minus half. So x to the power minus half means you have 1 over under root x. Now when x goes to 0, this function become unbounded. Okay, so therefore this is the improper integral of third kind, and because of this infinity it is first kind, and because of 0 this is first kind, second kind. Okay, so these are beta and gamma functions, and in the seventh problem you have to find out which of the following statements are true. Okay, so you have to see, notice that here we have p comma q and here we have q comma p. So this problem says that if you change these things from pq to qp, what will happen? Will they become same, or will they not be equal? What will happen basically? Okay, so let's find out what will happen if you change them. Okay, so what is beta p comma q? By definition, this is integral from 0 to 1 x to the power p into 1 minus x to the power q dx. Okay, and what is beta q comma p? So q comma p is little bit different because here you will be taking x to the power q and 1 minus x to the power of p dx. So are they equal? Can we say that these two are equal? Okay, to see that they are equal, what we will do, we will change the variable, put 1 minus x equal to t, then you will get minus dx is dt, right? Okay, so let's put it here. So this will imply x is equal to 1 minus t. Okay, so in the place of x we will write 1 minus t to the power q. In the place of 1 minus x we will write t, so this is t to the power p. Now dx will become minus dt. So dx is minus dt. So this is minus, and what is the this range of the integral? So when x becomes 0, t will become 1. When x will become 1, t will become 0. So this is our integral. Now we'll just change this value. This is integral is from 1 to 0. Now we'll make it 0 to 1. If you make it 0 to 1, this minus sign will disappear, right? So you will have 1 minus t to the power q into t to the power p dt. Okay. Now, because the value of the integral depends only on the endpoints, right? This value of the integral depends on 0 and 1. It doesn't depend on the variable t or x. So instead of 1 minus t, we can write 1 minus x to the power q, so 0 to 1, and t to the power p, no, x to the power p, and dx. Now note that this is our beta pq, right? This is exactly beta pq. Okay, and hence the correct answer is first one. So it says that the beta function is symmetric about these arguments. Whenever you exchange them, the value of the function will not differ, will not change, even though we are changing p and q, right? Notice that we are exchanging p and q. This p is going here and q is going here. Okay, but the value of the function will remain same. Okay, so eighth problem. This is about gamma function. Okay, so this gamma function is a function of second improper integral of mixed kind, right? And it is saying in the problem, it's saying that if we transform the variable x to this variable y, then what this integral will become? So basically, we have to put y equal to e to the power minus x in this integral. Okay, let's see what will it will become. So what is gamma of n? It is 0 to infinity e to the power minus x and x to the power n minus 1 dx, and we have to take y equal to e to the power minus x. Okay, so if we put y equal to e to the power x minus x, what we'll get? Dy is equal to minus e to the power minus x dx, right? Now e to the power minus x is just y, and what is dx? Okay, so let's write minus y dx. Okay, so this will imply, okay, from here what we'll get x is minus x is equal to log y, and from here what we will get dx is equal to dy by minus y. Okay, now we will put these two values in the integral. This is 1 and this is 2. Okay, so e to the power minus x becomes y, x will become minus of log y, and power n minus 1, and dx will become minus dy by y. Okay, now note that when x will become 0, y will become 1, right? If you put x equal to 0, y will become 1. So we can write here 1. And when x goes to infinity, y goes to 0. So the limits are from 1 to 0. This, okay. notice that this y will cancel with each other, and when you change these limits of the integral, you can change this limits, right? You can from 1 to 0, you can put 0 to 1. Okay, so you'll get a 1 minus sign extra, and minus log y to the power n minus 1 and minus dy. Okay, so okay, these two minus sign, they will become plus, and you will have 0 to 1 minus log y to the power n minus 1. Okay, but this is not our answer, right? Because we are having log of 1 by y. Why? Now note that minus of log of y is same as log of 1 over y, right? Because this log have this property that log of a by b is same as log of a minus log of b, right? And therefore ln of 1 over y is log of 1 minus log of y. What is log of 1? So logarithm of 1 is 0. Okay, hence you have this equation, third equation, and therefore this integral will become 0 to 1 log of 1 by y. Okay, and to the power of n minus 1 dy. Now notice that your first option is correct, log of 1 over y to the power n minus 1 dy. Okay, okay, so we'll just end our live session here because it's already been time.
Yes, sir. There is no question. This is included in the gate levels for computer science.
Oh, what is your question?
Is it included in the gate levels of computer science? I mean, whatever we covered today, is it included in gate computer science levels?
I don't know. So this is course on calculus, right? It's engineering mathematics 1 course. So I don't know about computer science courses.
Okay.
Okay, so